Hey, there's good sound there.
It's Mickey Mouse.
Hey, so thanks for coming out tonight to the TECA meeting. We are spoiled for sure. My name's Scott Miller, by the way. I'm the current president of TECA. We are spoiled rotten tonight to have Saji Mathews here from AIC Heat Exchanger, all the way from Toronto. He's going to be coming up and telling us everything we need to know about heat exchangers, and probably more, I bet. Coming up.
Thank you for taking time off your schedules to hear me talk, which is not the most palatable thing after this wonderful meal. But I hope I would be able to share something that is useful to everyone. Firstly, my wife always complains that I speak very low. So if you can't hear me, give out a shout so that I can raise my voice. But I tend to mumble sometimes. Please remind me that I'm mumbling. I'm off on a tangent. Feel free to stop me if I'm speaking nonsense or if something is not clear to you. The idea of giving this presentation is to introduce you to, of course, heat exchangers, but also to introduce you to what goes behind the scenes when you get a heat exchanger in your hand. Now, I was racking my brains thinking of, typical speakers. They start off with a joke or maybe icebreaker, but for the world of me, could not think of any joke that pertains to heat exchangers. I mean, if somebody knows something about heat exchangers that can be used as a joke, please do let me know so that I can use it in my next LNL. And, very welcome to tell me all your jokes that maybe in some mechanical rooms you do get some jokes going that way. But let me give a small introduction about what we do. AIC Heat Exchangers, Advanced Industrial Components, started off in Poland in 1988 by a gentleman who was an extremely good engineer, but surprisingly not a very good salesperson. He had two brilliant sons, so he gave them the two factories. We started off as Sesspol in Canada, selling heat exchangers into US and South America, and of course in Canada. That was in 1998. We have this, we came from Europe with this unique kind of heat exchanger, which was called a spiral heat exchanger, which I'm sure when you think about heat exchangers, nobody would ever think about that. I do have some pictures of those, how they look like. But our company came out with that product, but we do have other products. We sell them, we design them. We have a team of 12 based out of Oakville, Ontario. We do design and we do sales, we do marketing. We also do lots of training. Training, some of them is basic, some of them is more involved when we talk to the engineers. And our heat exchangers in BC are being used right now. UBC is ours, SFU is ours, City of Vancouver, City of Surrey, Richmond, Westminster, and we are moving north to UNBC, and we are going further north into the gas and oil sector. We have, when you talk about heat exchangers, we are certainly not the number one that comes to your mind, but hopefully this will change your image of what we are, and hopefully this would be something new to you. My idea was to go to what goes behind the scene in selection of a heat exchanger. So when we go behind, they come in a wide variety. There are more than one type. And the typical question a person would ask, I'm not sure how many of you are familiar with heat exchangers. Okay, quite a few of you are. Heat exchangers, as the name suggests, it's an equipment that exchanges heat. The idea is to use something that would increase the effectiveness of heat transfer. Now, this is a term that is very similar to efficiency. Now, efficiency is used only with boilers or pumps, which actually use electrical or mechanical energy to produce energy. But heat exchangers don't produce anything. They only transfer. So whatever is provided to a heat exchanger, it will transfer very effectively. So the higher the effectiveness, and remember this, effectiveness is a mechanical term. It has some value. So when I say effective, it doesn't have, the same meaning as what people would understand from the word effect. Effectiveness typically is a value of, it's a ratio of the inlet temperature versus the outlet. There is a very involved formula how to calculate it. But typically, heat exchangers, or plate heat exchangers have values of 0.7 and above, which means 70% and above. And shell and tube heat exchangers have typical values below 0.5. So shell and tube heat exchangers are poor heat transfer equipment. Plate heat exchangers are better heat transfer equipment. Having said that, don't go out with the idea that, okay, I will rush out and buy plate heat exchangers, because there are always some pros and cons for every type of heat exchanger. There is no ideal design. As I said, there are two main types, shell and tube and plate type. Shell and tube can be shell and coil, they can be finned, they can be various shapes and sizes, they can be U-tube, they can be straight tubes, they can be with expansion joints, lots and lots of variations. But they all do one simple thing, they transfer heat. Now, plate type can be brazed plate heat exchangers, welded plate heat exchangers, plate and frame heat exchangers. All of them involved taking a bunch of plates, putting them together. If you put them together with nuts and bolts, they are called plate and frame heat exchangers. If you apply a copper braze on them, put it in the oven, cook them, they are called brazed plate heat exchangers. If you use fusion welding on the plates, they are called welded heat exchangers. Now, what type of heat exchanger should I choose? First, we look at what are the process conditions, available space, and economics. I don't know how you would rate these. Typically, people would say, let me have the cheapest heat exchanger. So price is right here. And people then forget the rest of the stuff. What is my process condition? What are the restraints that I have on the space that I use? So I'm trying to introduce this concept that you should choose your heat exchanger based on all three, not on one. You could always manipulate your process conditions in such a way that you get a cheaper heat exchanger, and that's the idea that will be introduced later. How do you manipulate your process conditions? What are your process conditions? What would be a process condition when you do heat transfer?
Flow rate and temperature.
Yes, a flow rate and temperature difference. The inlet temperature of a fluid, the hot fluid, versus the inlet temperature of the cold fluid. So these process conditions determine the size of your heat exchanger, and obviously the price and the material of the heat exchanger. Basic heat exchanger calculations involve this term, LMTD, logarithmic mean temperature difference. In nerd terms, LMTD, if I state this in basic English, it just means the temperature difference. But it's not calculated the same way as I would when I went for an interview, I was asked what does the rate of heat exchange depend upon. So I said temperature difference. So how do you calculate that? I said, okay, you take the temperature of the outlet minus it from the inlet, that is a temperature difference. It is not. There is a slightly different formula that we use, and it is actually a ratio of the inlets and outlets of both your fluids. You take a natural logarithmic mean of that, and that is LMTD. I have the formula, I will show it to you. It is just for interest, but remember, we manipulate that figure, that your heat transfer is directly proportional to the LMTD you have. So larger the LMTD, smaller the heat exchanger. Smaller the LMTD, larger the heat exchanger. So if you know the LMTD, if somebody tells you that your temperature difference is small, expect a large heat exchanger. If your temperature difference is large, expect a small heat exchanger. That's why if you have steam as a heat source, your heat exchanger will always be smaller. If you have something like an economizer that you use in your plant, where you have very tight temperatures, your heat exchanger would be massive. Cooling heat exchangers that are used in buildings in Toronto, you guys are lucky that in BC you don't have cooling heat exchangers. Those are massive, massive heat exchangers. Like some of them have 16-inch connections to have a delta T of 2 degrees. So LMTD is the most significant part of selection of heat exchanger. So again, I make a point. Larger the LMTD, smaller the heat exchangers. Smaller the LMTD, larger the heat exchanger. So directly proportional to the LMTD. That's one concept that you have to think about when you determine what you need as a heat exchanger. Now we have an LMTD. We have a temperature approach. Let us look at what happens to the size of the heat exchanger when the LMTD goes smaller. The first example, this is all based on identical temperature conditions. If you had a 20-degree LMTD, how do you calculate 20? 160 minus 140. This is one of those situations. We deliberately chose a situation where calculation is easy. Sometimes you could have 160 to 120 and 100 to 133, some odd numbers. Then it becomes very difficult to calculate the LMTD. There is a formula to calculate. But in this case, it's very simple because the rule says, the physics rule is that if the LMTD formula becomes 0, then you just take the direct difference between the temperatures. So in this case, it's a 20-degree temperature difference. So the LMTD is 20F. Look at the heat transfer area, 6.5 feet squared. Example 2, and this graph actually shows you how close you're approaching. So it's a 20-degree approach. You come to the next example, we have the same primary temperatures, but we have changed the secondary temperatures. LMTD of 5 degrees. Look at the size of the heat transfer area. It's now almost 7 times more. You can imagine how much more metal you need for this particular heat transfer. You have reached a much larger heat exchange. And then you come to the example 3, where your LMTD is 2 degrees. Example 2, LMTD is 5 degrees. LMTD is 2 in example 3. Look at the size of your heat exchanger. I'm sure many of you have come across a lot of clients who say that, you know, I want my temperature to be like this, so close. I have one guy from the US, I think somewhere in the Midwest, he wanted a temperature approach of 1.5 degree F. I am not sure why you need that. I mean, would it bother you if the air coming out of this place was instead of 72 degrees, if it was 73.5? Would it bother you a lot? It wouldn't bother me much. Or if the hot water that you get in your house, instead of it being 140 degrees F, if it came at 135, 134.5, would it make a difference to you? It wouldn't. Not to me, but it made a difference to him. And I gave him the price of the heat exchanger. I'm sure that he probably fell down, because that heat exchanger had a huge area, because to get that final 0.5 degrees, that 1.5 degrees, we had to add 100 plates. From the 2 degree F to going down to 1.5 degree F, I had to add 100 plates to make it work. Do you think it's worth it? Is it worth spending so much money to get to, maybe it's somebody's...
Money's not optic, then maybe, but otherwise not.
But if you have a reaction, for example, if you're doing industrial, I'm talking about HVAC, if you are doing industrial, let's say you have a vessel which produces red color, and this 1.5 degree difference would mean that your red color would turn into blue. Yes, in that case, you should worry about that temperature, but not for HVAC. But there are people who want that kind of difference. We do provide those heat exchangers, but at a price. So you see that from 45 feet squared, you have jumped to 175 feet squared. Now, we talked about shell and tube heat exchangers and plate heat exchangers. Now, you would think that, okay, I could use either of them based on my budget, I could use. But unfortunately, the physics of this geometry and the physics of heat exchangers would not allow you to choose them. You cannot use shell and tube heat exchangers for scenario 2 and 3. Shell and tube heat exchangers do not work with crossovers. So there is no way you could select a heat exchanger for this LMTD of 5 and 2. So when I say that, what heat exchanger you would like to select, your process conditions, your LMTD, and the material that you use matters. So in this case, you cannot, if you have a scenario 2 and 3, you cannot use a shell and tube. You have to go with only plate. Shell and tube heat exchangers, they are very versatile, they are simplest, you can use for a variety of conditions. Unfortunately, you cannot use them with crossover temperatures. There is a different type of heat exchanger called shell and coil heat exchangers, which we make. They are unique to us. These are intermediate between shell and U-tube heat exchangers and plate heat exchangers. They allow crossover temperatures, but they are not as effective as plate heat exchangers. You see shell and coil heat exchangers here in Pacific Center. I'm not sure whether you guys have gone downtown Vancouver. So that's heated using a shell and coil heat exchanger using steam. The constraints, I always talk about space availability, and you know downtown nobody would give you a nice big mechanical room. So shell and coil heat exchangers are just like piping. So you see the one on the left, and the biggest one we make is about 8 feet tall, and it takes about 2 feet of space. So that's the only thing they could squeeze in there. They couldn't put a shell and U-tube heat exchanger, which works with steam too, but unfortunately it takes up about 8 feet of space. They did not have the space. And so shell and coil heat exchangers, it's a compromise between shell and tube and plate heat exchanger. And then you come to plate heat exchangers. They are very compact. The smallest one we make is 5 by 8. Really tiny. You could have it sitting on a shelf somewhere, and it would probably heat up the whole room. If you have floor heating, a small tiny one would heat up the whole floor, this whole area. Very effective. They are used for snow melt systems. They are used for domestic hot water heating. They are used for radiant floors. They are used for space heating. Any kind of application that you have, plate heat exchangers are used. All the buildings in this area, in downtown Vancouver, everybody uses plate heat exchangers, except for some of the steam heating that you have downtown. For example, if you go to the stadium downtown, I forgot your BC Lions stadium. BC Place, sorry. BC Place, right next to it is a tiny little building there. Has anybody noticed there? They have a nice little power plant underground.
Creative energy.
Yep. So they have a steam plant there. And they are our regular clients. So they use a lot of these shell and tube, shell and coil type of heat exchangers. Any questions on types of heat exchangers?
Sorry, I have a question. Is the shell and tube and shell and coil, are they similar in performance?
The shell and coil has a higher effectiveness than shell and U-tube. As I said, shell and U-tube is the lowest effective. Shell and coil would be somewhere about, probably in the 0.55 range. And the highest effectiveness is for the plate type of heat exchanger. So this is the first step you take. What type of heat exchanger would you select based on your process condition? And we talked about process conditions, the LMTD, temperatures, the fluids that you use. For example, if you had salt water somewhere, sodium chloride in the system, what would you do? So what do you have to think about the fluids you're using? Of course you have to, because that determines what material you end up using finally to make your heat exchanger. So my next presentation is what types of materials are available out there to make heat exchangers. So what are the common heat exchanger materials? Now that you have selected your design, let's say that you wanted a shell and U-tube heat exchanger and you wanted a plate heat exchanger, and they needed a custom-made heat exchanger of some design. So what material would you use? What are the materials available? Metals. Everyone knows about metal heat exchangers. Of course, there are plastic heat exchangers. Did anybody know about plastic heat exchangers?
David does.
There are plastic heat exchangers out there. We actually make we used to make a pool heat exchanger out of a plastic shell and titanium tubes.
Hey, I know that once. It leaks.
Yeah. We stopped them because plastic doesn't work very well. So our model has changed completely to titanium, and the cost is the same now because we now make it completely welded titanium. So you can have metals, carbon steel, the cheapest material that you can guess. Almost all the shell and U-tube heat exchangers have carbon steel shell with copper tubes or stainless steel tubes. So if you use carbon steel as the base, stainless steel 304 is 4 times more expensive. Stainless steel 316. Are people familiar with these terms, 304, 316? These are just grades of steel. Stainless is obviously better than regular steel. Stainless doesn't corrode as easily as carbon steel. So stainless steel 316 is 6 times more expensive. Marine grade stainless steel is 12 times more expensive. Marine grade comes under different names, SMO254 and AL6XN. AL6XN is the US name for that product. SMO254 is the name from Europe. So if you see those names, they are marine grade stainless steel. And they are 12 times more expensive. Copper is 15 times more expensive than carbon steel. Titanium is 18 times more expensive. Then you get super alloys. Can anybody name a super alloy? Inconel, yes. There is nickel 2000. Then there is Hastelloy, Seeds 276, and with tantalum, you can go more exotic with niobium and etc., etc., etc. You just think dollar signs in big letters. But surprisingly, we have sold a heat exchanger to a company called Mosaic in Saskatchewan. They needed a solution which would, they had these exotic chemicals, something that would withstand the corrosion of those chemicals. So finally our design was titanium tubes, carbon steel heads and shell with Monel cladding. And that heat exchanger cost $1.5 million for two. And the idea is that we provided a solution, so somebody sat on the project forever. So in July, somebody realized that they needed a heat exchanger by September. And imagine if you make it in Poland, it's not going to come here in a few days. So we had to fly it. And that heat exchanger, massive, really massive heat exchanger, it is called an NEP 42. It was 42 inches in diameter. That heat exchanger managed to fit, there's only one airline that could take it, that was Lufthansa, and we managed to make the cutoff by 50 kilos. But we did deliver the heat exchanger and it's working.
How bad was the freight bill?
$40,000.
Bugger off for $1 million.
What about the heat transfer properties of the different, like for example, copper versus titanium?
Copper is probably the best. Somebody did point out to me that copper is 17 times better at heat transfer at the same thickness. At the same thickness, but remember that we are talking about conduction. Heat transfer in heat exchanges does not take place through conduction. It's through convection. So what plays a bigger role in heat transfer in heat exchangers is the turbulence. So that's why when you have a coil, that's how we get more effectiveness. We made this design to be so turbulent that it doesn't matter what the rate of heat transfer is. For example, copper, it transfers 17 times faster, but unfortunately, copper does not have the strength to be made into coils. You don't get copper coils which would be stable in a vertical heat exchanger. It can only be stable when you have baffles holding them in a horizontal heat exchanger. So shell and U-tube heat exchangers typically are made with copper. But the problem, even, I told you, their effectiveness is only 0.5, even though we're using copper. So they are not the best of solution because unfortunately heat transfer is not by conduction but by convection. Yes, you have a question.
17 times what?
Than steel.
How about stainless steel?
They are approximately the same because it's the same metals inside. But because it contains nickel and chromium, that sort of is lower than iron. So carbon steel might be a better bet. But unfortunately, in that, the problem with using carbon steel is that because it's so poor, it has such poor resistance to corrosion, you have to have it so thick that unfortunately you end up with a very bad heat transfer.
Makes sense.
Because the thicker the plate, the poorer the heat transfer. So heat transfer coefficients that we calculate depends on the thickness of the plate too. So if you have a plate heat exchanger and, okay, somebody had an engineer who wanted 1 millimeter thickness for the plate. I said, God bless your design, because 1 millimeter thickness would have a really, really poor heat transfer coefficient. You need thin plates and you need turbulence. So typically plate thicknesses are 0.4 minimum and it goes up. You could do 0.8. I have sold a heat exchanger for lean and rich glycol with a 0.8 thickness of 0.8 millimeter thickness.
Wait, is that 0.4 millimeter?
Yes.
So the
16,000.
or
16,000,
16,000.
yeah. That's thin.
It is thin. So that's typically what is used. But surprisingly, the pressure rating for such thin plates is 150 psi. That is 1.03 MPa. So those plates are quite strong. I mean, to get a rating of 150 at 250 F is a big challenge, but 0.4 is the minimum you can use. So titanium can work with, it's a stronger material, so you can work with thinner titanium, but unfortunately the minimum that you get is in 0.5. You don't go below 0.5.
20,000.
So titanium surprisingly is becoming more and more popular. The problem with titanium is that it is a restricted substance. So if you need to buy titanium, you have to sign a waiver with the US government saying that you're not selling it to North Korea, Iran, and Cuba, and etc. etc. So it is a restricted substance. So if you make titanium heat exchangers, all of us have to sign it. And the latest restriction that has come in is by the US government again. You cannot buy copper from certain countries. So all of us have to sign this document saying that we did not buy. We actually have to provide proof that they have the name of every smelter in the world. Can you imagine? Their database includes every smelter in every part of the world. So you have to name the smelter of your copper. In our braze plates, we have such tiny bits of copper, and you have to trace not the copper, but the tin. Because of this problem with Congo. So these are things that we have to work in the background so that we don't end up with a metal that came from the wrong sources. Titanium that ended up in Iran, you are in trouble.
It's better.
So I was mumbling, sorry. But super alloys, we do make things like SS317, stainless steel 317, stainless steel 204. If you need something more exotic than that stainless steel, we make them. We can make plates out of it. They are heat exchanger materials, rubber gaskets. Everybody is familiar with rubber gaskets. What types of rubbers can you use? NBR, which is butyl butadiene rubber, nitrile butadiene rubber. So this is the most common, easily available. It's used, I think your tires are made out of the same material. That's the same thing that we use in heat exchanger. NBR can be used for most applications. You can also have EPDM. EPDM is more resistant to chemicals, especially chlorides. If you have an application which has, we are talking about how your process fluids affect what is selected. So EPDM is used in swimming pools. If you have seawater applications, EPDM is a better choice than NBR. But if you are using something that has compressor oil or hydraulic oil, EPDM can never ever be used because EPDM dissolves in all these chemicals. So if you have any organic fluid in your system, do not use EPDM. There is White-on that can be used. Is anybody familiar with White-on?
I put my O-rings with it.
White-on is Teflon.
It is.
So Teflon is also used as gasket material. really the best resistance to chemicals. Actually, the UBC swimming pool has white-on gaskets on it. White-on is so expensive that your gaskets would be the same price as the whole heat exchange. So you would typically doubling the price of your heat exchanger if you ask for white-on.
That would be in a plate heat exchanger or a plate and frame?
Yes, and also for your shell and tube heat exchanger, there are gaskets between the head
On the flange?
and the shell on the flanges. You can have them as white-on. Typically, they are not white-on. They are pressed fiber. So they are the cheapest. But we do have a range of sanitary heat exchangers which come with white-on gaskets. So they do add to the cost. For sanitary, especially a food application, you cannot use EPDM or NBR. You have to use white-on gasket. Types of heat exchangers, again, material selection. There is plate and frame. The plate thicknesses vary between 0.4 to 1. We talked about one engineer asking for 1 millimeter plate. I can provide those. But they typically, the lowest you have is 0.4 to 1 millimeter. Gasket thickness is between 1 millimeter and 5 millimeter. Brazed plate heat exchangers. Plate thickness is between 0.2 and 0.4. You never ever get thicker plates in brazed plate heat exchangers because if you ever try to braze thicker plates together, they just collapse. They don't stay stable. Brazing material thickness is 0.1 to 1 millimeter. Brazing materials can be copper. Everybody has heard of copper brazed plate heat exchangers used everywhere. I'm sure that you are not even aware that the refrigerator that is behind you has a heat exchanger in it. Or your water heater at home has a heat exchanger in it. So these heat exchangers are so tiny you can fit them into anything and everything. Brazing material can be copper, can be nickel, and also now stainless steel. We have produced, I think we are the second company after Alfa Laval which actually has a stainless steel, brazed stainless steel heat exchanger. So, but also surprisingly, copper brazed heat exchangers have the highest pressure rating. By a strange anomaly, copper when brazed onto stainless steel becomes the strongest possible bond. Copper itself gets completely transformed chemically that it doesn't behave like copper anymore. And the pressure rating of a copper brazed heat exchanger can be as high as 9,000 psi. We actually make a range which goes for carbon dioxide cooling, which is rated 9,000 psi. And we stock units with 2,000 psi in our warehouse in Oakville. Nickel brazed, surprisingly, though nickel is a stronger material than copper, unfortunately the nickel brazed material is only 150 psi max. Stainless steel brazed, the max you can get is 200 psi, nothing more. So brazing, surprisingly, copper is the best. Types of heat exchanger, again, shell and tube. Tube thickness varies between 0.5 to 3 millimeters. The tubes typically are 3/4 size and the thicknesses vary between 0.5 to 3. Oil industry, typical, if you have API 660 rated heat exchangers, then you need to have 0.065 millimeter inch tubes, that is 1.6 millimeter thickness. Whereas typical HVAC, shell and U-tube heat exchangers, they have much thinner tubes. I think they are in the range of 0.035 inches, which is much less than half of what the oil industry asks for. Shell thickness is between 2 millimeter and 50 millimeters. Tube sheet thickness. Do you know what's a tube sheet? So we have this tube bundle, a bunch of copper tubes that are U-tubes. So they are U-tubes, a whole bundle, but they have to be either expanded or welded onto a thick carbon steel plate, which actually holds them in place. I told you that copper does not have strength. So to make copper strong enough to remain in the geometry that you want it to be, you have to expand it into this thick piece of metal. Usually carbon steel, you can have it titanium or you can have it as stainless steel, but they are up to 2-inch thick. So this tube sheet is very, very crucial in the operation of a shell and U-tube. There are additionally baffles in a shell and U-tube heat exchanger. They can be between 0.19 and 0.5 inches. How to select the proper material. So everything should be made as simple as possible, but not simpler. It's a quotation from a very famous person. Can anybody guess?
It's Einstein, wasn't it?
Yep. And it is very true. We put it in so that we sound wise. But this is very true of the heat exchanger industry. We should make it as simple as possible, but not simpler. Because sometimes you need to add a little more complexity into the process, because typically that reduces your price. And if you look at the economics of making and selling heat exchangers, I could make a really simple heat exchanger, unfortunately it will not work. Or I could make a super complex heat exchanger, which I could not sell. Plates, gaskets, brazing tubes. The metal thickness, rubber thickness is crucial. Choose materials that meet those requirements. I don't know. It depends on what your client wants. The shells, tube sheets, baffles, the thicknesses have to be standardized based on your corrosion resistance. Do you know that typically engineers ask for, or the Association of American Society of Mechanical Engineers, ASME, asks for particular corrosion resistance for all the material that is used in heat exchangers? If you use carbon steel, minimum 0.5 millimeter thickness has to be added to the thickness for corrosion resistance, because carbon steel is really, really bad. I actually had an experience today. I went to visit a site and I had these beautiful heat exchangers, stainless steel on the outside, specifications from the engineer. Stainless steel here, stainless steel there, stainless steel on the side, stainless steel on the bottom, on the top, everywhere stainless steel. And then we have this heat exchanger which we open up, full of rust. Why? Because the pipes are all carbon steel. And then we talk, the pipes are all carbon steel. Why go to all this effort to make this nice, beautiful, shiny heat exchanger with stainless steel when your pipes are all carbon steel? And then I pointed this out to the site supervisor that there is rust here. So he said, maybe your heat exchanger rusted. No, you specified stainless steel 316. How would it rust? Then that would be, there would be, and it has that stamp, ASME stamp on it. You know that the ASME stamp is granted based on proof of material too, not only the pressure temperature rating, but also proof of material. You have to specify the material and it will be as per ASTM so and so. So that is proof. Then the guy says, you know, what can I say? Just look there. So we are in this rain, standing out on the side. There was a whole pile of pipes without any covering, without anything. They are going to use it on site into one of these beautiful buildings in one of your famous institutions here, all rusted. Please select your material based on what your process conditions are and what you're going to intend to use it for. And this is going to be connected to a domestic hot water system.
You mentioned corrosion inside the heat exchangers. How about erosion?
Yes, how many of you are familiar with erosion? Okay, so what is erosion?
Pitting due to turbulence and fluid.
Yep. Erosion is basically pitting caused by velocities of fluids. It's basically turbulence. Turbulence creates friction in the system, and that friction actually scrapes the metal off from the plates or the tubes of the heat exchanger. So we talk about corrosion, but erosion is also a very big issue when you deal with heat exchangers. We actually had a case with Husky, with the shell and U-tube heat exchanger. They actually measure the erosion rate of every one of their heat exchangers. Not heat exchangers, every part of their system. Pipes, valves, anything they use in a system. And we actually had to prove to them that the tubes that we use, the nozzles that we use, are Schedule 80. What was requested was Schedule 40, so we had exceeded the, so Husky has a lot of money, so they employed a person whose only job throughout the year is to measure this. And there is actually a term that is used, it's called rho, the Greek letter rho, which actually measures erosion. So erosion is a big thing in the heat exchanger. If you see a shell and tube, typically, you will see that after a few years, maybe 7 years, 8 years, you will see that something that was a straight tube like this would end up like this. So what has happened is that either your water or your steam has exceeded the velocities required, and it has eroded the sides of your tubes, and it maybe in a couple of years that whole thing is going to fall apart, not because of corrosion, but because of velocity. Velocities are good for heat transfer because low velocities reduce the rate of heat transfer. It also promotes scaling, but unfortunately high velocities can erode the heat exchanger. Especially when you're working with steam, you have to look at the velocities that you're working with. Low pressure steam demands large connections because velocities can exceed a certain limit and destroy your heat exchanger. So this is the thicknesses, how the thicknesses matter. Any questions?
Well, can you tell the difference between a corrosion and erosion if you took one apart?
You would have to probably do some kind of complex analysis to do that, but typically corrosion would occur only with fluids that are corrosive. Now, when I say fluids that are corrosive, when you're working with stainless steel, one of the most corrosive things you could work with is chloride. Stainless steel is readily corroded by chloride. And where do you find chloride?
Ocean.
Sorry?
Seawater.
You don't have to go there. This water has enough chloride to corrode stainless steel.
This stuff.
Yes, sir. What do you think they use to destroy all the bacteria? It's chlorine.
That low level would cause a problem with stainless steel.
Yes, if you let it dry. Why do you get this?
And concentrate.
You take this, these are stainless steel 3 or 4. I'm sure that anybody who uses a dishwasher, you will see this discoloration when you use certain types of cleaners. Where do you think it comes from? That's corrosion. So that water that you use along with the detergent is quite enough to destroy stainless steel 3 or 4. And I'm surprised that we allow utensils to be made out of stainless steel 3 or 4. Hospitals do not allow such kind of material, only 316. But 316 is also corroded by chloride, but to a much lesser extent. So 316 is used in swimming pools up to a level of 130 parts per million of chloride. If you exceed that, stainless steel is corroded fast. Yes?
Yeah, I was just wondering about double wall heat exchangers. I don't know if you're still going to talk about that or not.
Yep.
But yeah, just about the efficiencies and so forth.
So when we talked about heat exchangers, we touched on just the types of heat exchangers, but one of the variations you could have is a double wall heat exchanger. Double wall heat exchangers can be tube style or tube style. Tube style, much less popular. Why would it be less popular? Because remember we talked about effectiveness. You already have an effectiveness of less than 0.5 and then you add a second tube with an air gap in between. Heat transfer is based on, as I said, convection across the metal wall. Now you have a second tube inside separated by an air gap, and you know that air is a very poor conductor of heat and that air is not moving. So if you need heat transfer, you're literally, this air gap is basically something that prevents any kind of heat transfer. So with double wall heat exchangers, with plate heat exchangers, which we have measured, it's about a 40% drop in effectiveness if you go double wall. Shell and tube, more than 50%. And but the code in BC asks for double wall heat exchangers for domestic hot water heating. So every installation needs to have it.
Is that 50% of the 50%?
Yes.
That's not everywhere though.
That
Only
means
some
squat.
cities.
Sorry?
It's not everywhere. It's just some cities.
It all depends on who the inspector is.
Vancouver was one.
West Van,
Burnaby.
West Van.
It all depends, because even in Ontario, it all depends on the inspector, because we had a case here at, I think 4 years back. We were talking to the city inspector. They actually passed a bylaw that made the city, every contractor had to remove all their single wall heat exchangers. Based on what? I do not know. But they made everyone remove their single wall heat exchanger. I correlate this with the whole technology of domestic hot water heating or hydronics is actually a product that came from Europe, because they do not have the luxury of cheap energy that we have. For example, forced air systems. There is no European country which has forced air systems. Everyone has in-floor heating or radiator panels or something, water-based system, not air-based system, because air is an extremely poor conductor of heat, and gases do not conduct heat very well. If you use water, because it's denser, it has a higher mass, specific density, it will conduct a lot more heat. But we do not use that. And then additionally, we have passed this law that all the heat exchangers for domestic hot water needs to be double wall. It's a good way of protecting your centralized boiler systems, but unfortunately, who is paying the price? You and me.
Homeowner.
So further to that then, I guess, how real is that, or how real do you guys feel it is? The whole point of it is to prevent cross-contamination of domestic, in this case. How often are these things failing, plate or otherwise?
Well, to tell the truth, you know, when you work with heat exchangers, they are mechanical equipment, they will fail. But I haven't come across a complaint from Europe that they have contaminated drinking water.
Because the pressure differential, we can't.
That's the thing. You have actually pointed out what we should be, the policymakers should be looking at. You should mandate this thing about pressure difference. California actually passed a law saying that if your system is below 30 psi, you don't need double walls.
Yeah.
Because if your boiler is working at below 60 psi, why do you need a double wall? Because your domestic hot water would go into the boiler rather than your boiler water going into the domestic hot water system. they are not trying to protect your boiler. They're trying to protect the city water supply.
It's because of a rule from IAPO, which is the International Inspector Code. Most of these are countries that don't have inspectors. And that rule got brought up for the war. And then some Canadian cities read that book and started adopting some of those.
Oh, you should see the new regulations that have come up now. And they are coming up with NSF 61, low lead, then NSF 372. So many restrictions, and all of them. And Vancouver is probably going to be the first city that is going to adopt anything that comes out of US. So they are the first ones who are going to adopt this. And but that just increases the price of the products you buy, because each of those testings, for example, we are part of AHRI 400 certification for heat exchangers. Now that means performance guarantees. Do you know how much does it cost to do this testing every year?
10, 20, 30 grand, I don't know.
No, that is just for testing, but you have to continue your testing. So suppose you need to fly people out to your factory, you pay for it. Do you think that the manufacturer is going to not pass it on to the clients? Everybody is going to pay a higher price, but unfortunately that's what the rule is. And now, of course, it's created a level playing field for everyone, because people used to undersize the heat exchangers by 40%. But now everybody has to follow the rules, and if it is not AHRI 400 certified, you cannot install it in any other buildings in Vancouver. So that's a new rule that has come in. That is performance certification. But it costs money. Same thing with NSF 61 testing. It starts at $25,000 for one heat exchanger. So suppose you have 20 models, you can imagine how much money you're going to spend. Any more questions?
Did I understand that the first part of your presentation that you cannot use steam with a plate type heat exchanger?
Yes, you can use it, but we don't get it warranty.
Why is that?
Because first when you look at steam condenses. That's the energy that you're trying to extract, the energy of the latent heat of condensation. So that's what you're trying to extract from condensing steam. But remember that when you condense steam, this is the volume of the vapor that has come in. As soon as it condenses, it reduces, it becomes dense, and it becomes a liquid. What happens to the rest of the space? It's a vacuum. And so vacuum obviously means that the walls of the heat exchanger will collapse inside. That if you have a plate heat exchanger, I said you have brazing. Why do you braze it? To keep it stiff. Why do you have nuts and bolts holding the plates? To keep it stiff. Now, if you have a vacuum inside such a system, it's going to pull everything inside, so it's going to collapse the plates. The plates are going to warp and be destroyed. Whereas you have a shell and U-tube heat exchanger, which has a U-bend, which will accommodate this expansion and contraction caused by the condensation of vapor. So they are the best choice. Though they have poor heat transfer coefficients, they are the best choice. When you have a steam system, always go for something that is shell and coil or shell and U-tubes kind of heat exchanger, because they have that intrinsic capacity to bear this expansion and contraction of the structure of the heat exchanger. So the last one we have is how do I manipulate? Okay, we first looked at process conditions, etc., etc. Then we decided what material we want. Now we have a heat exchanger. Now, how do I make this big heat exchanger into a smaller heat exchanger? What can I do to give best value to my client? How do I play around with the physics of it? How do I play around with the LMTD or etc., etc., to make my heat exchanger smaller? So I'm just going to touch lightly on what what can you manipulate so that you end up with a heat exchanger that is best value for your client. So when you look at, now we have starting on the process of designing a heat exchanger, I always insist that anyone who contacts us for the request for a heat exchanger provide us with flow rates, inlet, outlet temperatures, total heat load, and types of fluid. Why is it important to have types of fluids specified?
Yes.
What kind of fluids do we use normally?
Water, glycol.
Steam, yes. I have also seen, this sort of covers around 95% of the fluids that we encounter. But there are people who use methanol, geothermal systems. Then there are people who use ammonia, refrigerants. Then there are people who use high temperature fluids, for example, terminal. Has anybody worked with terminal? Terminal is used if you do not want to have a steam system. You just heat up terminal to 500 F. I think its boiling point is beyond 500 F. So you have ultra high temperature fluids. These are produced by, I think, DuPont. They sell a whole range of terminals. You can use them for high temperature heat transfer. But based on your fluids, your heat exchanger size will vary. We did a hospital job in Ontario, designed in 2010, delivered to the client in 2011. 2012, I do get a call. You know what? We going to install this heat exchanger. We just noticed that we're going to run 50% glycol instead of water. So, do you think this would work? And so that heat exchanger was maybe about 7.5 feet tall and about 249 plates. So we did some calculations. Do you know how many more plates because of the 50% glycol? 140 plates. Fortunately, there was enough expansion capacity to add those plates. What the cost to the client? Those plate addition cost more than a brand new heat exchanger. $11,000 just to add those plates. Why so? Because in our economy, labor is not cheap. Typical labor costs for plates, either adding plates, cleaning plates, in Ontario right now it's running $950 per 8-hour shift per person. So you need typically 3 people for one cleaning of a heat exchanger. You can imagine the cost of adding plates or cleaning plates or whatever you do. So it costs the client one more heat exchanger just because an engineer forgot to write glycol on the specs. Fortunately, they didn't hold us responsible. Otherwise, you can imagine what would have happened to all of it. So fluids are important. Now let's go back to what we talked about, LMTD, etc. This equation, I'm sure everybody is familiar with this, if you're doing heat transfer.
That WCT over time, yeah.
So this is what is known as theoretical heat transfer. So Q is heat, M is mass, Cp is the capacity of the fluid that you have, heat capacity of the fluid, and delta T is obviously the temperature difference. This is what you're trying to achieve. So as a client of mine, you will come and tell me, I have this equation with me. That's what you're trying to tell me when you supply me with flow rate. When you say flow rate, that's my mass. When you define your fluid, when you say that it's water or glycol, you have defined the Cp. And then you tell me inlet and outlet temperatures, you have given me the delta T. So I have stuff from you, which you never imagined you gave me, that will fit into my equation. Now this is theoretically, for example, Gary told me I need MCP delta T of this much. And that comes out to be 250,000 BTUs per hour. So I did a calculation based on the mass, flow, the flow rate, the temperatures, and the CP of that fluid that was defined. This is theoretical. This is in the best case scenario, this is what is possible. What I give you is another equation which we use. This is Q is equal to UA LMTD. Remember we talked about LMTD some time before? That LMTD is a logarithmic mean temperature difference of my material. What would that material, what would it do? Now Gary told me he needs 250,000 BTUs transferred, so I put that on the left side of the equation and then go and search in my inventory what material would have the U value, that is, U is the heat transfer coefficient. A is, remember we talked about LMTD? The larger the LMTD, the smaller the area. Smaller the LMTD, larger the area. That is where it comes from. So it is directly proportional. They are directly proportional. So I go into my inventory and I look into what material would have the heat transfer coefficient which would best suit the 250,000 BTUs. And that's how we fit a heat exchanger to your requirement. Let's say you told me, no, I need 500,000 BTUs per hour. Then I would go back and search in my inventory for a heat exchanger which would do 500,000 BTU per hour. That's a term I use. I call it sizing. Why is it sizing? I'm just searching in my inventory and picking up a size and saying, okay, this is the heat exchanger that does 500,000 BTUs per hour. So that's the term that is used. I'm sure some of you have heard, because everyone does sizing of maybe pipes or ventilators or exhaust units or pumps. That is sizing. So for us, sizing means I fitted a heat exchanger to what you theoretically told me to do. So these are the two most basic equations, and we play around with this. For example, if you have a large LMTD, I can give you a small area. Your heat transfer is possible with a smaller area. You have a small LMTD, I have to increase my area to make it work. So this is that mysterious equation that I was talking about. Lots of things there, but just remember that it includes hot side inlet, cold side inlet, cold side outlet, hot side outlet. So it's a mix of those temperatures. We use this equation to make our heat exchangers work, and you can manipulate this. We manipulate these equations to make it smaller or bigger. So what all can I manipulate? I can manipulate the material because of the U. I can manipulate the size of the heat exchanger because of the surface area. And I can also manipulate the temperature difference and make it bigger and smaller, because the LMTD would go up and down based on how I manipulate the temperature. So let's do some optimization. So optimization can be done on price, dimensions, performance, pressure drop, and parallel and series configuration. Let's look at each one of them. The basic thing I can do, let's say that I come up with a heat exchanger and you say that doesn't fit my budget. What can I do given my constraints that I have to give you a heat exchanger of a particular type? I can play around with the type of plates. You can see that there are two types of plates. There is thermal long and thermal short. Thermal long plates they have better performance, and thermal short plates have inferior performance. But unfortunately, they also have, why we would not always give you thermal long is because thermal long means higher pressure drop. If your pumps cannot handle it, You cannot get thermal long. So I can play around with the number of plates this way. Like I don't give you all thermal long, but put in some thermal shots, make your heat exchanger smaller. Your heat exchanger becomes smaller, lesser number of plates, lesser price. This is one way you can play around. Then go to dimensions. It is possible for us to increase the height of the heat exchanger and come up with a smaller heat exchanger. You have space constraints, no problem with the roof height, but problem with the width or the length. We can give you a taller heat exchanger and make it work. So you should be aware that we can play around with dimensions to give, or sometimes you don't have enough clearance on your roof, just cut off the legs. We can do that. We can cut off the legs, make the heat exchanger shorter, it still will work. You can choose a, for example, you don't have enough height, like for example, we have a heat exchanger to deliver in downtown Toronto, specified, drawings are approved, order is released, heat exchanger is ready to be delivered, then another question from the client, not the client, the engineer actually. It has to go through a standard door. The heat exchanger is 7 feet tall. It is 24 inch, not 24 inch, 28 inch door. How do you get the heat exchanger? I mean, the heat exchanger would fit inside the mechanical room, but unfortunately nobody ever looked at the door. How do you get it down? We actually had an interesting situation while delivering heat exchangers to one of the downtown building. The door is okay, everything is fantastic. Unfortunately, there's no ramp. The heat exchanger has to go down the steps. It weighs 470 pounds. How do you take it down steps, and that to curving steps? So these are interesting things about dimensions, which as engineers and people who actually work on the field should check. I had this strange question asked so many times. Would it fit a standard door? Why would it fit? Because when you approve the drawing, shouldn't you be checking the dimensions? We actually had to take down a wall, like an entire wall, to get the heat exchanger. And that time we had to cut a hole in the roof to pull the heat exchanger inside, which was for a school. Can you imagine? They poured concrete and then cut a big hole in the roof on the roof of the basement to take the heat exchanger down, because somebody forgot that it doesn't go through the door. We can, as I said, I can adjust the floor supports to adjust the height. I can cut, plate heat exchangers. If you look at the top of that image that you see there, there is a bar on top. There's a bar on the bottom, which is, the top one is called the carrying bar. The one at the bottom is called the guide bar. They actually can be cut to whatever specifications you want. People are afraid to ask us those questions. I'm telling you, you can tell us, oh, I don't have space at the back of my mechanical room. I don't have enough space. I can cut it for you. So that's one way you play around with dimensions to find the right heat exchanger for your plant. It is possible to get a smaller heat exchanger by altering temperatures. I told you I can play around with the temperature by a very small amount and get a smaller heat exchanger. This are numbers actually from something that we did some time back. So the size, heat load is 150 kilowatts. The size of the heat exchanger is 12 inches by 30 inches. Now look at what happens. We change the temperature by 0.5 degrees on the cold side. It's 52.5 to 86.5, same heat load. Do you think it would matter to anybody if it is 86.5? I don't think it matters to anyone. Look at the size of the heat exchanger, 10 inch by 20 inch. I cut off 10 inches from the height of the heat exchanger. And what would be the price difference? A 37% drop in price. So this is the way you can play around with the equations, the LMTDs, the area, etc., to get to a size which is economical. I mean, I could have, some engineers are very adamant, they say, no, I need 87, then you pay the price. You have to pay 37% more, but you can go with the smaller heat exchanger. What does it matter? Because it is still doing its job. So it just needs a little flexibility. Pressure drops. This is my greatest grudge against engineers who work in specifying heat exchangers. There is actually a spec out right now for 1 psi pressure drop. You try to do a 1 psi pressure drop. It's good for your system, but unfortunately it's not good for the heat exchanger. Because remember we talked about how effective heat transfer works. Turbulence? Turbulence is needed, and turbulence creates pressure drop. So you need some pressure drop to make this work. If you do 1 psi pressure drop, you're also increasing the number of plates, because number of plates or the length of the tubes, we have to adjust that to get it to work. More the number of plates, more the price. The longer the heat exchanger, you're paying more. But do you think that we can manipulate, instead of 5 psi, can we work with 5.5? You would see the great difference in that 0.5 psi pressure drop difference. Your price would come down by, sometimes by half. We have specs, I think most of the engineers have now agreed that 5 psi is a reasonable pressure drop in Vancouver. So 35 kPa and 50 kPa, and I surprisingly saw a spec out for 75 kPa. 75 kPa is close to 10 psi for a small heat exchanger. So they are learning that it doesn't really matter. The other option we have is to have units in series and parallel. Have you seen units in series and parallel? So it actually, when you have a problem with, you might find a solution when you have large flows to split it into 2 smaller heat exchangers. You can make it work much better at a cheaper cost than having 1 large heat exchanger. Because larger the heat exchanger, the larger the port size, and then you have to have a really large number of plates to achieve what you want. If you have very close approaches, you can actually have 2 heat exchangers running in series to make it work. So these are options that you have in optimizing your size. And the last option that I can offer is, why don't you go for a 2-pass unit instead of a 1-pass? You can go 2-pass, 3-pass, 4-pass, 5-pass, 6-pass, 8-pass. Same size of the heat exchanger, same price for the
How
heat
does that work on a plate heat exchanger?
It's the same thing, it goes through 2 passes. You design the plates in such a way that there is an additional pass which is 2 pass. We actually have, I have a case study where we designed a heat exchanger with 8 passes to make something work for heat recovery. And that's a project we have sold multiple times to greenhouses where they are trying to recover heat in pasteurization. So, any questions?
Do you sell heat exchangers in the dairy industry?
Yep.
For pasteurizing?
Not for pasteurizing, but for CIP systems. But we do have a type of heat exchanger which is used for pasteurizing. You know, pasteurization has multi-section heat exchangers. So you heat up your fluid to, I think, 60 degrees C. And then the next section, in one frame, you have 2 heat exchangers. One heats it up, and the other one, in the next stage, cools it down. So we do have pasteurization. But this pasteurization I was talking about is used in greenhouses to pasteurize their fertilizer feed to the plants. They have to pasteurize that. Shall we go on to a couple of case studies, and I can hand it there. There's a whole bunch of, this is the first case study, a whole bunch of specs given by a client of mine about 3 months back. Don't read all of it, just read what's in red. So their main problem, if I could explain it, they have a heat exchanger which they purchase at great price. It's using seawater, and they're cooling it on I think at a cruise ship or something. So unfortunately, it doesn't work. The whole thing is of all this explanation here that it doesn't work. And they have clearly specified they want a shell and tube heat exchanger using shell side river water, tube side is condenser water. River side water is an estuary, so it has salt contamination. So they told us that they need this to be 20 inches in diameter, and maximum length is probably 72 because it's a ship, they don't have too much space. So this is solution one. Remember the diameter of the shell. So we sized shell and U-tube heat exchanger in technical terms. They are called as BEU type, 14 by 60. And I think many of you would know what is a BEU or a BEM, BKM, BEM, AEL, etc. So one of them, our U-tube heat exchangers are called BEU technically. So we sized them. Shell diameter they wanted 20 inch, I gave them 14. Max length they wanted 72, I gave them 70. But there was a problem. It needs more cooling water than available from the existing pumps. They can only provide 240 gallons per minute from the existing pumps. And if I keep to this size, the most efficient design, it needs 330 gallons per minute. So they don't have pumps. So they can't change the pumps. They don't want to buy the pumps. So, and the price, and they had specified material. They want copper-nickel and they want titanium. Look at the price difference. What are the problems? Cost and flow. They don't have the budget for this. They specified all these exotic things, but when the price comes before them, they don't have the budget. They don't have 32,000 to spend on the heat exchange. And the flow, obviously they can't supply 330 gallons per minute. This is not a solution for the client. Solution number 2. So we go back to the drawing table and then gave them a solution with 10-inch diameter and a total length of 104. Cheaper heat exchanger, fits their budget, 15,800 Canadian dollars. Does fit their budget. And remember I told you we could manipulate the playing around with the LMTD? That's what I did. I got a better heat exchanger, smaller heat exchanger by having a better delta T. But unfortunately it doesn't fit the space. So that's a second iteration which failed. This is the third solution we came up with. He didn't ask for it. We provided a plate and frame heat exchanger with titanium plates. Titanium plates are superior to copper-nickel, better corrosion resistance, works with estuary water, with salt contamination, no corrosion problems, nothing. Look at the length, it's only 22 inches. They gave me 72 inches. I gave them a heat exchanger which would fit within 22 inches. And what's the price? Only $8,000.
What about all the contaminants, particulates and stuff in river water?
They have a very good strainer system because otherwise it would never work in there. They have a very good strainer system that eliminates all sediment. Because they had already specified that their strainer only allows less than 0.5 millimeter particles to go. So that's why we actually suggested it. And
All was good.
yeah, it was solid. But you know, one of the things they never told us, remember my example of the door, which was never ever obvious to anyone. This heat exchanger has to go through a hatch. I was just trying to think, how will you ever send down that 14-inch or 20-inch heat exchanger through that hatch? And this heat exchanger, because it's only 22 inches, goes through the hatch perfectly. They never even bothered. That's the thing, that when you do get something from a client, they forget something very obvious, that this has to fit through a tight space. They never ever told us. But this does. So it was a perfect solution for them. And this is what they finally went with. Forget about what they specified. That's why when you do heat exchangers, you just need to remove blinders, think outside the box, come up with a solution that works for the client. Sure sale for a heat exchanger. And there's a second one, which I thought might be interesting to you. We are talking about the pasteurization. So when you need to do pasteurization, there are two ways. One is by heat treatment, which is mechanical means, and the second one is by chemical means using ozone. Most people prefer the ozone way, but unfortunately it is not the best possible solution. Ozone is produced through a corona discharge process. So 85% of your energy input is lost. So it's not environmentally friendly. It requires pH and temperature controls. Ozone is toxic. And various byproducts of ozone produces carcinogenic materials. Do you need that? And you have to constantly monitor bacterial levels in water. This is what is being used in the greenhouses right now in BC. In Ontario, they have changed because they don't use chemicals anymore. This is what they do. This is a solution which has multiple tiers. You have pasteurization being done by the vertical shell and coil heat exchanger. Remember we talked about steam and how we need coils. So they use a boiler which produces steam, which the heat exchanger, the vertical type, condenses steam to produce water of 205 degree F, which is used in the pasteurization tank. A lot of energy is used in heating up the water. And this water, once the pasteurization is done, it has to be cooled down and it is sent out to the plants for, it's a fertilizer feed, so it has to be cooled down. What do you do with that energy that you use for cooling? So the solution was the feed water that goes into the pasteurization tank is heated up, preheated using the fluid that comes out. So instead of using any coolant, you use your feed to cool down your pasteurization. And that heat exchanger is if you look at the connections, it's an 8-pass unit. So it makes 8 passes through the heat exchanger so that you get a delta T of almost 1 degree F. So that 55 degree water is actually being the temperature approach is it's almost extracting everything from the coolant. So this is a solution we came up, and we have, I think, sold in the last few years probably 8 or 9 systems with this two heat exchangers, which is for them a huge saving on the ozone, because remember the 85% of the energy that is used to produce ozone is a waste. So they are recovering almost, I think, around 80% of the heat that you use for heating. So this is the solution that we gave them. And it works. So these are things that we have to remember, that if you think outside the box, you have a solution that you will always sell. I don't know if anybody works with greenhouses, but if you don't, then you can take the solution along. So if you compare, 85% of the energy is lost, 3 to 4% of the input energy is lost using heat exchange. pH and temperature controls needed for ozone, no pH monitoring needed. And the bacterial levels have to be monitored in treated water, but you don't have to monitor anything once you exceed heat of the pasteurization liquid to 205. All the bacteria is killed. It's guaranteed. And no chemicals are produced or required in this solution that we provided with hydronics rather than with chemicals. So we can actually replace chemicals by using heat as a substitute. We actually use in many solutions, for example, pasteurization of pharmaceutical products, heat is used. Cleaning of food equipment, CIP systems that we use, they're all based on a temperature of 160. Once you heat up water to 160, all the bacteria is dead. This is a solution that is now standard in almost all. They don't use chemicals. They only use heat to destroy bacteria. So that's it from me. These are FAQs. If you needed any answer to any of the FAQs, let me know.
I have one question in general. When do you switch from a brazed plate heat exchanger to shell and tube with regards to pressure drops, and what applications? Swimming pools use shell and tubes typically because of large water volumes.
We use plates when you need high effectiveness. Now, having said that, what typical applications would we come across? For example, I classify typical hydronic applications like floor heating or snow melt systems or garage heating or space heating. The temperatures are such that the best solution is a plate heat exchanger. Plate heat exchangers also can be easily manipulated for pressure drop, because the principle of a plate heat exchanger is that it's parallel flow. Because once the fluid passes through the nozzle, it comes into plates which are all parallel. So you have one plate here, next plate, it just grows. But each of them is a parallel path, so you're distributing the pressure now. So there is no pressure drop. The only pressure drop that you get is because of the passage of the liquid through the plates. The path that it follows, the pressure drop is created by that. So if you have a pressure drop issue, it is good to have a plated frame heat exchanger, because it will remove the barrier that you have, because it's a parallel path. Whereas you have a tubular heat exchanger, you have a series path, because each of the tubes is very long, even if it's a U-bend. So you're going to create more pressure drop. The longer the tubes, because there is no parallel flow, this is a series system, so you will increase the pressure drop. And you, like for example, if you go for a 2-pass, 3-pass, 4-pass, in each of those passes you're increasing the pressure drop. It's because they add up in series. So when you go for a solution which requires less pressure drop, please do not add passes or increase the length of the tube or increase the height of the plate heat exchanger. Then you would have a problem. Any other question?
All right.
Saji.
Thank you, and thank you everyone for